I want to welcome all of you to the Valley of the Shadows of Advanced Quantitative Research. It's a pleasure to have every one of you. Today, we want to begin formalizing multiple regression models. We've looked at sample regression. We've gone through the derivations. We've examined the intricacies in Excel and in R. We have understood some of the assumptions of regression. We have checked the expected value of the error term being equal to 0 practically. We understand the fitted model. We understand the predicted model. We understand the actual minus the predicted gives you the residual or the error. We want to extend the sample regression to multiple. Multiple regression have got several independent variables. Independent variables are the same as the regressors, and they are also the same as the explanatory variables. Remember, I've been saying that we can use the UI, epsilon I, or EI for the error term. Okay, this is a simple multiple regression model because the independent variables are just two. Now, the independent variables usually will have I. The I stands for individuals. The individuals is not human beings. It can be groups, it can be countries, it can be companies, it can be items, it can be human beings, it can be cars. So if you want to assess different type of cars, it's different kinds of entity. And so that I can move all the way from 1 to n, where n is the total number of individuals that you're looking at. In a dummy regression, some of these individuals are not numbers, they are categories. We shall examine them also. So we are looking at a basic cross-sectional model where the I represent the individuals, which means that all the individual items we have, all the independent variables, they change across individuals. They don't change across time. So there's no subscript called time. All right. Now, this is a typical regression model in front of you. It's a multiple regression model. Now, my interest is for you to be able to think and tell me other factors. We all know that the wage of a person, the salary of a person, is affected by the person's education. That your education may have an influence on your age. That your experience may have an influence on your salary. That your position in the company may have an influence on your salary. That your ability that you have may have an influence on your salary. Question is, the other factors that can affect wage, but those factors have not been captured inside these independent variables. All of these factors are considered within the error term. They are within the error term. They are within the residuals. That's why they are unobserved. That's why they are disturbance terms. That's why they are unobserved heterogeneity. Okay. Who can tell me other factors that may affect the wage of a person? Think about the factor to be quantifiable. If you can't quantify it, it must be a dummy. Okay. Factors that can affect wage but have not been included here. Who can think of factors like that? Who can tell me one factor? Let me see the first person who's going to talk here. What other factors can affect the wage but have not been captured here? And by the way, that's the same thing you would do with your work, in your thesis. Desmond.
No, please, gender.
Gender, to what extent?
You said?
To what extent?
As to whether it's a female occupying the job or a male, some people prefer a male to a female. So once the female, they get sometimes they don't really value it that much. So, but maybe that's what they have. So they beat down the price sometimes. They wait sometimes.
Okay, give me a typical example.
For example, maybe you need a sprayer, okay, and then you get a female sprayer. In the first instance, you actually be thinking, can this female do the job? So you wouldn't like to actually set a high wage for that until maybe you get to see the experience and other things come on board before you would actually start to trust.
Okay. These days, it's not that simple. These days, I mean, it's difficult to
Yes. I know it's
actually bring it. That's why I'm
because
asking you
because of the
so
gender
many.
equality issues.
All right, let's put gender aside. Let's go to another relevant. In fact, give me relevant factors. Derek.
Okay, so Doc, I'm looking at government regulations. So something like minimum wage laws, overtime regulations, and other government policies will definitely affect the wage levels.
Perfect. No question about that. Emmanuel.
Doug, I'm considering the sector of employment, whether it is a private sector or a government sector.
Perfect. Perfect.
Also, I have one more. With our experience, we believe that those who have been exposed to what is called managerial level or non-managerial level, position may be different from this managerial level or non-managerial level, which I believe strongly that it may have a high influence on one's salary.
How different is that? I thought it's the same.
From our experience, no. For example, those working at the bank, we have the big boys at the ESCO level. Those are the MD, DMD, the finance director, those big guys. Their level is quite different from the general level that we may call manager level. Those are executive level. But here we have a position. You may be, for example,
It's
may
okay.
be.
It's okay. I get you. The temptation will be that you may want to justify it significantly, but it all boils down generally to position.
Okay.
Amy.
Doc, please, what of labor market's demand and supply of a particular skill?
Okay, give me an example.
So, for example, let's say they need software developers. So, if they are in high demand and their supply is very low, I think it can affect the wages.
All right, so let me just pinpoint that labor union is a factor. Labor union. If you belong to a union, your wage might be different from if you don't. Albert.
Yeah, look, if the person is an expatriate, the company would have to pay for his accommodation and other, so that will make his wage very high compared to the locals.
Yeah, this is for specific companies. Okay. I get it, for specific companies or for specific sectors. So the risk factor comes in. So ladies and gentlemen, the key point is that if there are other factors that should be considered, but you did not consider them, you will have a smaller R square, and that will affect your results. Let's take another example of a multiple regression. The blood pressure of a person is affected by the age, the weight, the stress, and the pulse. Of course, the other factors that can affect the BP, which have not been captured here, who can tell me other factors that can affect the BP but have not been captured here? Nobody should mention broken heart. Nobody should mention broken heart. Which other factors can affect blood pressure that are supposed to be captured? But this analysts have not yet captured them, which may affect the results. Samuel.
Yes, please, Doc. I believe diet is one of one of the factors, like
Very good.
what
Very
the
good.
person eats.
Don't worry, don't worry. When you say it and I don't believe it, that's when I will ask you to explain. So don't try to explain. So diet is one. Nanajwa.
Doc, sometimes it could be hereditary in the bloodline of the
Very
family.
good. Genetics is another. Emmanuel.
Dog, I'm proposing the sex. Whether
Thank you. It's okay. Okay, so sex type can affect blood pressure. Okay, Derek.
Doc, I'm thinking the race.
Race can affect blood pressure. Next. So you guys are all tempted to want to explain and justify.
Doc,
Yes?
high cholesterol level.
I'll go into your weight. You see, there's a connection, there's a very high multicollinearity between cholesterol level and blood pressure and weight, and fat and all of those things. But you can also single it out. So yes, it has a factor. And I want you guys not to think about only factors that will increase it. Derek.
Doc, I think your sleeping pattern.
No. Richard. Richard. Gertrude.
Not smoking.
What?
Smoking.
Doc. Sorry, I couldn't hear you.
Smoking.
Smoking. Okay, good. Samson.
The strength of your immunity or your immune system.
It goes into the hereditary and all that. Joseph.
Lifestyle.
Everything they said is lifestyle. Everything here is lifestyle. So please don't generalize it. Noah.
Doc, alcohol consumption.
Alcohol. Everything that enters into your body, alcohol, smoking, they are all part of diet. Nanaya.
Doc, smoking.
All right. Thank you. Ladies and gentlemen, I think that people have gotten to a saturation point. Now people are repeating the same thing that have been said. So that is how you are able to capture other factors. Now let's go to the next one. Quantity demanded. The quantity demanded of a product is affected by the price of the product, by the income of the product. That's whether the good is a normal good or an inferior good or a gifting good or necessity or ostentatious, whatever. Okay. It can also be affected by the advertisement. The advertisement can affect the quantity demanded. Sometimes the more advert you do, likelihood of you getting more demand. It can be affected by whether the good is a complement or a substitute. So if the substitute of the good is up, people will switch away from buying the substitute and they'll come to this good. But of course, there are other factors that can affect the quantity demanded of a particular product. Nobody should mention taste and preferences. Which other factors can you think about that can affect the quantity demanded? Joseph. Joseph.
Doc, you mentioned my name.
Your hand is up. That's why I mentioned your name. All right. Emmanuel.
Doc, special trade discount and credit terms.
Special what?
Trade discount and credit.
Special discount or credit can affect the demand. Okay. Okay, yeah, that's viable. It still goes into the price though. Let me go to Samson.
I think when the goods are near expiration, when they're about when they're about to expire, people may not want to buy them.
Okay, good. I like that thought process. What else? Inflation can affect the demand for a good. Gertrude.
I think you've already said it. Hey.
I
I
knew you were
wanted to
going to say
say,
that. I've already said it.
no, I wanted to say seasonality, like seasonal.
But seasonality has got nothing to do with inflation. Seasonality has got nothing to do with inflation. Seasonality means that if we are in a Christmas period, demand will go up. If we are not in a Christmas period, demand will come down. So seasonality is good. Okay.
Yes, please.
What else? Let's go to Samuel.
The cultural practices.
Everything is culture. It's difficult to even measure it. Think about things we can measure well.
Okay, so religion.
Religion, yes, I'll buy that. Okay, religion can affect demand. For example, when you look at our Brukutu data set, okay, we are talking about alcoholic gin, and you can see that there are different religions that are there. By the way, nobody's going to mention occupation and then and location. There are other religions there, and you can see that Christians are likely to go for more alcohol than Buddhists. So religion can affect. What else? Get to your hand is still up. Derek.
Doc, government policies.
Very good. I was looking for that a lot. Government taxes, policies, subsidies, all of these things can affect the demand of the commodity. So you got to know these factors that can affect demand. Good. Now, the first one you see is the regression model. It's a specified regression model. The second one you see down here is the estimated regression equation. Remember, the first is the specification. The last one is the estimated equation. Question: who can tell me the difference? There are two main differences between the regression model and the estimated equation. Who can tell me the two main differences? Look at it with your eye. The difference will pop in your brain. What is the difference between the first bullet and the last bullet? Adami.
So, Doc, I'm attempting. One is the absence of the error term, which is not present. So in the first, the regressional model, there's the error term, but in the estimated model, there's no error term. And secondly, in the regressional model, while it caters for individual scenarios, the estimated model caters for the generalized. So it is more of a predictive model, which is used to predict outcomes. So those are the two that I observe. Thank you.
Okay, you got one out of the two. The last one is not correct. Who can tell me the second difference between the estimated regression equation and then the specified regression model? Nanaja.
Doc, so the beta values have been specified in the second case here. And then
what do you mean specific?
So for instance, with the
Be
first
specific with the word, because the word specified means that you have everything here in the document is specified.
So Doc, in the first equation, we have them in I's, meaning they are for generality. But then for the second one, it's been given. We are looking at wage being equal to 150, which represents the beta not from the first one. And then there's 0.85 representing education, beta 1 from the first one. That's what I'm trying to say.
Yeah, but that is not the ice that you mentioned. So you're confusing two things. The last one, I could have still brought the ice. The I attached to it, but that's not the real difference. What is the real difference you want to talk about, Bendita?
So for the second model, the parameters have been estimated. So we have the numbers there.
Yes, so it's the numbers. The numbers are there. In the previous specification, the beta parameters have not been found, so there are no numbers. So numbers in one, no numbers in the other. Okay, You need to know this because we will use estimated one for prediction. Now, let's go back to our Brukutu data set. Suppose we are to specify the regression model for the Brukutu data set. Yes, Benny. If you have to specify the regression model for the Brukutu data set, how would you have specified this regression model? If you were to specify the regression model for the Brukutu data set. So specifying the model means that, just a second, let me just show the entire screen. Specifying the model means that you are bringing the beta parameters. So this is a data set. And normally when you're writing a paper, a thesis, an article, what you got to do is to specify the model first. How do you specify the model here? What would you write to indicate that you've specified a model? Who can guess? Who can try? Normally, you use the headings to do the specification, something.
So first, you will want to know, you will want to define the variable, the dependent and the independent variables. Then you show their connection.
So how will you do it so that I write it?
Okay, so if I want to use the quantity demanded as the dependent variable, I can say that Q is equals to beta naught plus beta 1 price, which is P, plus beta 2 C, and then beta 3 with M.
Yes.
The other ones are, how should I call them? There are a different set of variables that will not be used in this case.
They will. Why are you saying they will not be used?
Well, they will be used in specific cases when we want to test for something different, as in the location. We want to test whether the location has an influence on. Well, in that case, we can use them though. But because they are not numerical, we may have to change them into ones and zeros to make them able to be used in this case.
To be able
to use them in the case of this model being specified, because this is urban, rural, they are not numerical. So if we want to do so, then we may have to change the urban to say 1 and the rural to 0. In that case, we can now add
we have done. So let's try it whether you remember. Noah.
Yeah, Prof. So I think you will add them, but you will not add them in terms of location and occupation and all that. You add them in terms of urban, rural, teaching, fishing, the individual.
Yeah, making me excited. So what will you write?
So you write plus.
I've done the plus.
So you do plus B4.
What is E4?
Beta 4, sorry.
Beta 4, okay.
Let's say occupation teaching.
But occupation doesn't come first.
Okay, location urban.
So you do lock urban. Just use the name as it's been given there, lock urban.
Okay, lock urban. Then we have plus beta lock rural.
Why did you just move to lock rural? Oh, okay. You are looking at the other one.
Yes.
Okay. So that will not be correct if you do that. If you do both for lock urban and for lock rural, why? Kingsley.
Okay, so sorry, Prof, you do lock.
No worry, you think, take your time, drink water, and then come back. And then let somebody take.
Yes, Doc.
Yeah.
Yeah, so I agree that will not be correct because yes, they are dummy variables, but there is the log OCC and REL, those are the main variables. And yes, we may have a reference variable for them. So we use as they are here. So location is locked. And when we estimate it, is the interpretation that will determine whether it is urban or rural.
Good. So in this case, which one has been dummied with a 1? And which one has been dummied with a 0? With what you see on your screen, which one is the dummied of a 1? And which one has been dummied as 0? Noah.
Doc, teaching is dummied
Not
1.
teaching. We are still on location.
Okay. Urban is 1.
Okay. And then?
Rural is 0.
Okay. How did you know that?
The coding, the coded
yeah.
sheets.
But when you're looking on my screen right now, which one? You can choose any one of them to be your dummy one. Because in this case, there are 2 levels. Okay. And because there are 2 levels, it means that the number of dummies will be 1. But if there are 3 levels, the number of dummies will be 2. If there are 10 levels, the number of dummies will be 9. So write this down somewhere. The number of dummies is always equal to 1 less than the number of levels. So if you write a dummy for 2 levels, like in this case, location, urban and rural, you don't need to do for rural. Like my good friend said, you got to talk about the urban in connection relative to the rural. So you don't write lock urban and then write lock rural. You just write lock urban. And then you will always have rural at the back of your mind each time you mention lock urban. So in the case of occupation, the number of levels are how many? You can tell me. How many levels and how many dummies? Occupation. Occupation. Joseph.
So we have 3 levels.
Mm-hmm.
The teaching, fishing,
and trading.
And then trading.
Okay, so how will you write the first one? Samson.
So because there are 3 levels, they will have 2 dummies.
Mm-hmm.
And in that case, if I take teaching as make it 1, then fishing and trading will be 0. Then when I take fishing also as 1, then trading will also be 0 for the second one.
Okay. So when you are writing the beta 5, you start with occupation teaching. You got to have it at the back of your mind. Which one? At the back of your mind, which one you are going to consider as the reference category? The reference category is always one of the levels that you decide to choose to be. You got to choose. Okay? You got to choose. It doesn't spoil anything. Any one of them can be chosen. Okay? Just be consistent. So in this case, because I have teaching, I decide that I'll create a dummy for teaching. So you create a dummy for teaching. And then you create a dummy for the next one, or the next one you will feel comfortable. I feel comfortable with making occupation trading as my next line of action. So in this case, and I'm done. So in this case, which one becomes my reference category? Fishing. Fishing. So it means that each time I talk about occupation teaching, I'm saying teaching relative to fishing. Each time I talk about occupation trading, I will say trading against fishing. So fishing is a reference category. The good thing about all this is that our software will select which one is a reference category easily for you. So you are good to go. That leaves us with the next one. Oh, in fact, this one is, oops, this one is not beta 7, but it's beta 6. Okay. Beta 6. So this is beta 6. And so the next one will be beta 7. Okay, and that will be the religion, which will be real Christians. Okay, religion Christians. And then the last one is beta 8. And the next religion I choose to select religion Muslims. So in this case, which one is a reference category for religion? Which one is a reference category for a religion? Yeah, who's going to tell us? Which is a reference category for religion? You remember the last religion? Derek.
Buddhist.
Okay. After that, you should now add your plus the error term. Plus the error term. Remember, you got to bring, of course, the I for under each independent variable. So let me show you how this was done, okay, in the slides. So this is your religious specification. This is the specification of the Brukutu Ventures cross-sectional model. Guys, look at it with every muscle inside you. This is what you sometimes see in journal articles. You sometimes see. This is a simple cross-sectional multiple regression model. This is how you specify it. And in your assignment, I have given you a very tedious one to dance with. And so you will have to do a kind of a bit of writing, on the specification of the model. So please understand it. Without the error term, there is no specified model. The error term is very important. Next, look at the regression model in a matrix form. This is a generalized matrix form. But this one is not a matrix form, actually. This is a specific. X1 is one specific independent variable. X2 is another specific independent variable. Xk is another one. If you combine these things into a matrix, who can remind us of how it was? The Y will all be put together, and the X will all be put together like this. So I will now put all the Y's together and have something, one for them, okay, like a Y, capital Y. Then I'll put all the X's together, have one. The Y is an M by 1 matrix. So there's one column, just like the arrow. Look at the arrow, there's also one column for the arrow. And then the most important ones are the independent variables and the coefficient attached to them. Independent variables are n by bracket k plus 1 matrix. And then the beta is k plus 1 and then by in 1 matrix. So that is how you convert this into the matrix form. This is how it was actually to convert it into a matrix. Okay, now pay attention here, guys. Today is pure theory, and it's very important. Sometimes in a regression, you will have to interact, moderate, mediate some confounding variables. You would have to take the logarithm of a variable. You would have to square some variable based on prior knowledge, prior literature, based on prior knowledge, prior literature. And you got to use that to do it. Guys, you got to think and make sure that what you are deciding is justifiable. Else, forget it. So why do you have to log the variable? You have to log some of the independent variables, and you even have to log the dependent variable most of the times. Why? We'll look at that. Wow, we don't even need to look at that. The key point, okay, so let me ask you, why would you have to log some variables? Who can tell me? Samson.
So I think when they are in different measurement units, or when some of the variables are so large compared to the rest, you may have to log them to reduce the level.
It's a good point. It's one of them. What do you mean by so large? Give me an example, practical.
Okay, so let's say you are working with GDP growth as against the summation of the nominal terms, the summation of export and import, which is what we normally call the trade trade openness. You see that this one is in percentages, and the highest it can reach will be 100. The other one can go as much as anything, and so and they are both they are also not in the same measurement unit. So you may have to log them to make it possible to do your
Okay, I lost him in the end though. I think that he was making some laudable points. Who else? Apart from the fact that you want to standardize them instead of normalizing them, okay, what else? Well, you take the log of some variables in order to put them into real value. Some of them are in nominal values. So sometimes you have nominal inflation, and in order to, if you don't have the real inflation, you take the log of the nominal inflation, and then you can interpret the scores in percentage terms. So take note, logging is important, but it's not everything you should log. What is one particular thing you should not log at all? Who can tell us? Which particular variable you should not log at all? Should not log. You should not log at all. Ima?
Zero or negative value, say.
Well, if you are trying to take the log of profit and that profit was a loss, you would have no choice that it will affect that particular negative one. But it's a particular variable you cannot log. You should not log. That variable is dummies, either 0 or 1 variables. Take note. Why? Go and think about it. Okay. Go and think about why you should not and cannot log those variables. Okay. Next one. You can square some variables, and the idea is to handle non-linearities. That's too mathematical or statistical. Why would you want to square some variables? Who can tell us? Why would it be necessary that you should square some variables? You square them because some variables rise, they get to a point, and they start falling. Experience. You take, for example, the experience of some footballers. They rise so high, now you can see that that of Ronaldo has entered into the diminishing marginal return section. So they rise, they get to a point, then they start coming down. They take a parabolic shape. They take a quadratic shape. And as what we call the N or U shape. They take that shape, which means that they can rise and fall. And when there's enough theoretical literature basis for that, you got to square that variable. You got to square that variable. And that is why we square some variables. You would also have to probably interact or moderate some independent variables. Interacting or moderating an independent variable is the same thing. Okay. So let's say that you have an independent variable x1 and you have another independent variable x2. Okay. You can interact them because sometimes they may have some multicollinearity features. Okay. And you can look at the effect of x1 on y separately, assuming that x2 is not there. You can look at the effect of x1 on y, given the presence of x2. So when x2 is there, let's look at the effect of x1. That is what that interaction you are seeing here means. So B1 will tell you by how much x1, given the presence of x2, influences the dependent variable. That's what B1 will do. That's what this B1 will do. So in some cases, you got to take a moderation interaction of the variables. Now, what then is mediation? Mediation. When two people are fighting. Yes, something.
Yeah, so I wanted to ask a question about the interaction. So assuming that the two independent variables that are being interacted, if they were not significant like separately, could they be interacted to become significant?
You said both of them are what?
If both are statistically insignificant separately, then by putting them together through the process of interaction, would that make them statistically significant? They interacted them.
Oh yeah. Sometimes they become statistically significant because you've interacted them. I've done some work right now, and they did that. Individually, one particular variable was not significant, but when you interacted it with some other variable, it becomes significant. I'll give you two examples.
Okay.
So, have you heard about corporate social responsibility?
Yes, sir.
Okay. So there could be a situation, I'm looking at the voluntary one. Let's say charitable giving.
Okay.
And you may think that we know that when companies give this charitable giving, the idea is that they do well. That's a presumption that they will do well. So when multinationals, foreign institutions, when they decide to do their, and this is interesting, in some particular countries, when they decide, the foreign institutions, when they do the CSR themselves, it is very significant. It has a significant effect on the donation. So, in other words, there will be a very significant effect of foreign people investing in or giving donation. When they give the donation to the people, the donation will have a positive impact. However, if they give the donation to the locals, the leaders, what happens? As we know, when the government, when the United Nations gives money to the country through the presidents and the ministers, what happens to the money?
It will likely not come to the individual, to the rest of the country. It might get its way to somewhere.
Yes. Okay. It might be wasted somewhere. However, when these companies, when these foreign institutions or these multinational operations, when they decide to give the money themselves to individual people, what happens?
They will supervise and ensure that the money is used for what it was
exactly
meant for.
So if I interact these two things, you will see that I have the foreign institution giving the money to the leaders, and now I interact it with the leader. The thing will not have an effect. But then when I do the foreign institution alone, the thing now have an effect. So that's a typical example of that sort of interaction. Most of the variables that can be interacted are dummies as well. So maybe a particular variable is not significant, or you don't even want it in the model, but you can interact that variable with a dummy variable to see the net effect of that variable. So that variable may not be great, but you may interact it with a dummy, and all of a sudden, it's great. Yes, Ima.
Doug, if you say interaction, what actually do you do to these two variables to get them interacted?
I think you have asked the smartest question today, and I was waiting for one of you to do. What you do is just what you see here. You multiply them. So let's say that you have a variable called x, and this variable is 1, 1, 0, 0, 1. And you have a variable called y, x2. And this variable is 24,000, okay, 26, 7, 8. Okay. Now, if you want to interact, you create another variable called x1, x2. And now you're going to take the x1 value, multiply by the x2. The first variable will be 20. The second variable will be 4,000. The next variable will be 0. The next will be 0. The next will be 0. Do you realize that the x1, x2 column has changed? The x1, x2 column has changed. Do you see that? And that is how the interaction is done, the moderation is done. Please, does that make sense?
Yeah, no, it makes sense. And the next one is that this time you will then use x1, x2 alone as one variable.
Correct. Okay. So you can run the model between y and then,
x1
y and then x1.
Okay.
And then you can run y and then the x2.
Okay.
And then you can run y and then beta 1, x1, x2.
Good.
And then you can have y beta naught, beta 1, x1, plus beta 2, x2, plus beta 3, x1, x3.
x1, x2. Okay.
Yeah.
Okay. Thank you very much.
So sometimes
you do this, so it means that the last one is the interaction, and also the third one is the interaction.
Perfect. You got it.
Okay.
You got it. So this last two.
The last two. Good.
That's how you do your interaction.
Okay.
The next thing you can do, apart from that one, is you can do mediation. And sometimes people confuse interaction with mediation. A mediator is someone who is solving some kind of a problem. So a mediator is like an interventionist. You are intervening. So what does the mediator do? Well, basically, mediation means that you are looking at the pathway via which a particular value is influenced. So you can look at the influence of X on Y. But then you realize that X affects Y through M. So you try and mediate. Now, what do we mean by that? It means that you will look at the X on the Y without the presence of M and look at the X on Y with the presence of M. That's mediation. Now, interacting or moderating variables, that rather means that you are looking at the effect of Y on M. And this effect of Y on M is conditioned on the third variable. Now, I've made a typo here, I think. Okay. This one is the same as the mediating. So this one should be mediation. Okay. I wanted to say the mediation. It's conditioned on the, no, it's the same thing, okay? It's conditioned. So this interaction is this that I've already explained here. So you are looking at the effect of x1 on the dependent variable y. But then now you've brought x2 there, so you have multiplied the two of them, and that is a moderating or the interaction factor. But then, so the two of them are together. But then when you're looking at mediation, the two of them are not together. Only one is together. Then you bring the other one, but when you bring the other one, they are not multiplying, but they are adding. So you will have B1, X1, and then you will have B2, X2. So the presence of X2, in the presence of X2, how is X1 affecting the Y? And that is the mediation. Let me give you a typical example for you to appreciate it. So you have an independent variable, which is workforce diversity. Workforce diversity affects creativity, which is a mediating variable before it affects organizational effectiveness, okay, which is a dependent variable. Now, you have this value here as a mediating variable, which you can take off. When you take off, you have no mediating variable. And you can look at the workforce effect on this. But then when you look at the workforce effect on this, there is a mediating variable you have not considered. And when you consider that before the impact of this becomes sensible, that is not the same as moderating. Okay. So moderating is you bring both workforce and managerial expertise, and then you look at workforce affecting the creativity, but then this one, the managerial expertise is present. And when that is present, that makes this, okay, these two moderating. Or in this case, the managerial expertise becomes a moderating factor. Now, when you look at size here and age here, they are individual. Nothing is influencing the other. And so they are direct exogenous variables. So you want to understand these things. You got to read more about them and appreciate them and understand them. Let's get a little bit more with the mediation. Suppose I want to look at the effect of X on Y. This is it. Suppose I want to look at the effect of X on Z. This is it. Suppose I want, how have I changed all of these things? I can't believe that. Okay. Suppose I want to look at the effects of a Z on Y. I should have brought Z here. Okay. The effect of Z on Y. Okay. That is this. So you have Y equals to beta naught plus the A prime X. Okay. Plus the BX. Should have made this one Z. Okay. Should have made this one Z. And I should have made even this one 3. Plus BZ. BZ. Okay. So in this case, you are looking at, you're moderating, you're mediating the effect of X on Y. You're mediating the effect of X on Y using the Z. So the Z now becomes a mediating variable. And these are very, very, very important. So when you believe that there is something, that the impact of something is real, only in the presence of another factor, then that factor becomes a mediating variable. Okay. So that is how you want to consider this. The last but one thing for today, I've spoken about it, is a dummy variable. And so what I've done is I indicated that the dummy variable is one less than the number of levels. So if the levels are, okay, let me ask you guys, if the levels are 7, how many dummies should we have? If the levels are 7, how many dummies, Ima?
Dog, 6.
And if the dummies are 8, how many levels do we have, Benedicta? If the dummies
Well,
are 8,
we'll have
how many?
7.
No, I just switched it. If the dummies are 8,
Oh,
how
if the
many?
dummies are okay. Okay. So we'll have 9 variables.
You have 9 levels. You have 9 levels. If the levels are 16, how many dummies should we have?
15.
And if the dummies are 16, how many levels do we have?
17.
Good. You got to know
17.
this. You got to be comfortable with this. You got to know these things very, very well. Okay. Note that the dummies are also called dichotomous variables or binary variables. Now look at this. I'm about to conclude about how you interpret dummies. Now look at these things. Is it an estimated equation or a specified model? What you see on your screen, is it an estimated equation or a specified regression model? Something.
I think it is an estimated equation.
Good. Who can interpret the coefficient of profit? Profit. We all know what profit is. What is the coefficient of profit? Actually, if you want to interpret a coefficient of profit, you got to have type and size in mind. Noah.
Doc, the profit will increase by will increase 20 times if the dependent variable is increased by 1.
No, that is not how you interpret it. Kingsley.
Yes, Doc, given type and size of the firm, it is expected that return on asset will increase by 20, so profit increase by 1 unit.
That's it.
Yeah. Okay.
That's how you interpret. You always have to say, given the other ones, how much will ROA, that's the left-hand side, change when the right-hand side changes? When you are saying given, the given should not include the very one you are about to interpret. So if you're about to interpret profit, you should not say given profit, type, and size. Because profit is what you're about to interpret. So you're not going to make it fixed. You're not going to make it given. Okay. So you say that on average, that's how you always start with. On average, given type of the firm and the size of the firm, return a 1 unit increase in profit will increase return on asset by 20 units. Now remember, profit is not a dummy, so it's a dynamic variable, so it's changing. It's not static, it's dynamic. So you can say that a 1 unit increase, then ROA increases by 20. So the 20 in front of the profit is not for the profit, it's for the return on asset. It's for the left-hand side. Now, the type of the company is 1 if the firm is domestic, or 0 if the firm is foreign. Who can interpret type? Who can interpret the type? How will you interpret that? Remember, type is a dummy, so within a year, it's not rising or falling, it's static. The word static comes from the word statue or stagnant, fixed, unmovable. Okay. So in that case, how will you interpret a static variable? Kingsley?
So, Doc, on average, given profit and size of the firm, the ROA is expected to increase by 30 if the firm is a foreign firm and it's a domestic firm, but 0 if otherwise.
That's wrong. You can try another. How will you interpret that of the type? Something.
Relative to relative to a domestic firm and given profit and size, a unit increase in the type, a unit increase, no, a foreign company will is expected to increase ROA by 30.
Okay, that's wrong. That's wrong. Emmanuel.
No, on average, given profits and size of a firm, the ROA will remain the same. Will increase by 30 if it is either a domestic or a foreign company.
That's wrong. Benedicta. Benedicta.
Yeah, so on average, given size and profit, please can you hear me?
Yeah.
On average, given size and profit, if type, sorry, if
Okay, you've tried. Samuel.
type
Yes, please,
increases by 1 hour to increase.
Okay, Benedicta. Thank you. Samuel.
yes, please. So on average, given profit and size, type domestic will have type domestic ROA will be 30 times more.
Okay.
On
Okay, relax.
Doc. Okay.
Relax. You just increased my blood pressure the way you start.
But please don't let your blood pressure go up.
The way you started the thing, I was dying for you. Take your time. The way you combine all the words together, my head started aching.
Yes, please, Doc.
So start properly.
Okay, so on average, given profit and size, the ROA would increase by will be 30 times more if the type is domestic as against foreign.
Repeat.
On average, given profit and size, the ROA will be 30 times more if domestic as against foreign.
If what domestic as against foreign?
If type is domestic as against foreign.
Type of what?
So type of firm is domestic.
So why don't you make that English? It's like you are stuck with some grammar. Okay, you are the one who has come the closest. So guys, the reason why I was saying that most of you were wrong is because you were increasing things. ROA will increase, ROA will increase, ROA will increase. No. Because type doesn't increase for ROA to increase. ROA will be different if the type is different. So first of all, you don't want to be using increasing of the type of the firm and then increasing the type of or increasing the ROA. So that's what the good friend said, that giving the profit and the size on average. Yes, Benedicta.
No, please. Does it mean that for a dummy variable, the symbol in front of the variable does not matter in the interpretation?
It matters. It
Whether
matters.
positive or negative.
Oh no, the symbol matters. The number matters. Okay? And I'm about to do that. The number matters, and the sign in front of the number also matters. In this case, they are all plus. But if it is minus, I will interpret it. I'll interpret it when it is minus, and I also interpret it when it's plus. But the key point is that on average, given the profit and the size of the firm, return on asset is expected to be, that's the word you guys were looking for, is expected to be, or is predicted to be 30 units more. That's what it is. It is expected to be 30 units more if the firm is domestic. If the firm is domestic than foreign. Now, why did I use the word more? It's because of what? The plus. But if the value is negative 30, you will say that return on asset is expected to be 30 units less if the firm is D, where D is what? 1. Because the D is 1, which is the domestic. If the firm is domestic, than if it is foreign. So that is how you interpret it. So the more or less is from the symbol, whether it's minus or plus. And the 30 is for the return on asset, the dependent variable, which it will be 30 more or 30 less, depending on the symbol in front of it. That's how you interpret it. You are never supposed to say that return on asset will increase by, as if this one has increased. You don't increase foreign or domestic. You don't increase from domestic to foreign. Neither do you decrease from foreign to domestic. These are dummies. You are a man or you are a female or a male. You are, at least within a year. You can't be changing every year. And that is how you interpret dummy variable. Dummy variable interpretation is very, very important. And especially when there are percentages, when the dependent variable is a percentage, that changes the way you interpret the dummy completely. Learning is a foundation. All right. So that is it. Okay. Learn how to do that. This is how we created the dummies. We changed them to 1, 1, 1, 1, 1. Okay. And I've shown you exactly how to do that. Okay. Now, remember the applied example that we have had. The applied example, you are writing a journal paper. The title of the paper was Determinants of Demand in the Alcoholic Beverage Industry in Ghana, the Impact of Location, Occupation, and Religion. We've gone through this before. The structure of the paper is normally like something like this: abstract, then you have introduction, literature, method, findings, discussion, conclusion, references. Normally, you have to collect data, and you have to indicate the kind of things you want to do, the methodologies. You may have to do descriptive statistics, contingency tables, visualizations. You may have to do correlations and with p-values. You may have to do, simple regression of a particular variable here, and then you go into the multiple regression. Okay. And these are some of the things I mentioned. You have to generate descriptive statistics and undertake univariate analysis, like checking the distribution of some of the variables. You may have to give some comment about the skewness of the dependent variable, whether it's bimodal, whether it's binomial, whether it's exponential, normal, log-normal. Okay. You may have to comment about the distribution, comment about the transformation of any of the variables. And then you may have to take a bivariate analysis correlation using heat map. You can do that, or you can use scatter plots. You can use scatter plot matrix. You can generate a correlation matrix with p-values and do all of that first. Then after that, before you come to the regression. So my goal is to run the regression of this data with you. So let's look at the data. This is a data set in our R. Okay, I'm going to run the data set in our R, and you can see that the data is right here in the console. So go to your command and run along with me. Run along with me. If you already have it, you know it. Run along. Now, so you have the gene equal to, I've just loaded the data. This data, you all have it. I want to run a multiple regression and watch the way R does it. Normally for Python, you may have to create the dummies, but R does it automatically for you, which is really cool. But I found a way in Python you can do it also really cool using the R approach, which is really, really cool. So this is it. I called my regression gene multi. You can call it anything. Remember, shorter letters are better. I use a linear model. The dependent variable is kill. You have the Greek tilde sign. Then you indicate the independent variables with a plus, plus, plus. Remember, each independent variable is added to the others. If you look at the last three, they are the dummies. You just add them the way you are adding the rest. R will automatically generate and split the dummies for you. And R itself will keep one of them not available. And that becomes the reference category. Okay, now let's run that and show the result. So this is it. I'm going to run that and show the results. This is a beautiful result that you have right here. Look at the results. The result will give you the linear model the same way as you had it. It will give you the residuals, the mean and the median of the residuals, the minimum and the maximum of the residuals. And then it will give you all the coefficients as well as their estimates, their standard errors, their t-values, everything that you need. You shall look at all of this, what each one of them means. Okay. Now, if you want, now what it doesn't give you here is the, one second, I think somebody's writing on my screen. What it does not give you here is the confidence interval. So if you want the confidence interval separately, you run this command known as round confidence interval gene multi. In other words, you generate a confidence interval using something called profiled likelihood, estimation. And the 2 here simply means that I'm correcting it to 2 decimal places. That's all it means. So I'm going to do the confidence interval for this very result. And when you run that, look down here. It gives you the upper and lower. Yes, Emmanuel.
Doug, please, after loading the data, the second command could not give me the expected values. It just came error object, gene multi not found.
Yes, so it means that you have to copy the data from Excel and then load it into the gene formula.
I have done, and the data has been loaded, say.
And you've run to see the results down there in the console?
Yes. It has given me the data about all of them as it was in Excel.
Okay. And then you run the command. Have you checked whether you use this tilde sign, use P? Have you checked all spellings?
Oh, yes. I copied it as it was. Let me just confirm.
Are you able to show?
Yes. Yes, sir. Yes, I can show, Doug.
All right, share the screen and let's see. Okay, so it says gene multi not found.
Yes, sir. The last one here. Yeah, Doug, here.
And the reason is partly because normally you're supposed to load, what do you call it? Is it CAS data? But before that, let me check something.
Okay, Doug.
Okay, go to the head of the data and let me see. Okay. Right, everything is fine there. So let's do library CAS. Maybe before the gene. before the 1, 2, 3, create a space and library cars.
I'm on the right path now.
Right. Library into brackets. Library into brackets.
Okay.
C. It will start coming CAR.
Yeah. Okay. Okay. Yeah.
Yeah. You seem to have not installed it. So go to packages and install it.
Okay. Okay. It is there. It was not checked, dog.
Okay, you check it, no problem.
Okay. Done.
All right. Run it and let's see.
Okay.
Doc, I didn't do the library cards, but I was successful.
Yeah, I don't know.
Yeah, now comes it. Dog, it has not come. It has given me the coefficients and the intercepts.
Yeah, but it's a challenge there. I need to understand. Run it first before you show the result. No, but when you run, come on. But you didn't add the summary. That's why. Take 25, 125, and go and add it. Click in front of 125.
Okay.
Exactly. And you run both.
Okay.
Don't highlight, just run.
Okay. Good. Look,
By the way, by the way, you should understand something. It's not about getting results. It's about knowing why your results are not happening.
Good.
You know, delete that result thing because the fact that you have brought it there, R sees it as an equation, as a command. But it's not a command, it's an instruction. So you have to bring a hash symbol in front of it. That's 126 that you have.
Okay.
You need to delete it. So you got to really eat the content of what, you see now when you put a hash symbol in front of it, it changes to green because it was seeing it as a code when it's not really a code.
Okay. No, thank you very much. I'm grateful.
Let's move. All right, so this is your result, and then you have your confidence interval. Now, there are two things I want you to take note. You can extract something we called the mean squared error. And let me show you that here. After you've run the regression, there are several analyses you can do. You can generate the ANOVA table. I don't normally like it, but some people like it. So, I mean, if you like it, you can do that. But before the ANOVA table, there are some few things you can do. But let me just go straight to the ANOVA table. So you can generate the ANOVA table with this, which you have in your slides. This will give you the ANOVA table. And you have all of them here. But the most, it gives you for each single one of them. But you will know that ANOVA itself, when you go to the regression here, okay, and then you run your regression, you will see that the p-value for the ANOVA is always the last one. Yeah. So unless you want to look at the ANOVA for each independent variable, then you can use the one I just did for the ANOVA table. You can also run the fitted model. Remember, the fitted model is the same as the regression, the predicted. And the fitted is this, 161 for the first one. If you can remember, the actual is different from the fitted. The actual is the one you have in the data itself. So in my case here, when you go to your Excel, the actual is 160. The second one, the actual is 200. The third one, the actual is 160. So the 160 is actual. It's predicted is what you have here, 161. The 200 is predicted. It's 198. The next one, which was 160, is predicted, is that And now when you find the difference between that actual and this predicted or fitted, that gives you the residual. So if I want the residuals and I run this next command, which you have in the slides, by the way, this is it. I'm running everything here, residuals, which is actual minus the predicted. Now, you can see that it gives you the residuals. Some are positive, some are negatives. And the goal is that these residuals the mean of the residuals should be 0. And that's what you want to confirm. So this next command will check whether the expected value of the residuals is truly 0. You can run it, and straight away you can see down there that there are 17 zeros before the -2. So it means that this is approximately 0. The residuals are truly, the mean of the residuals are truly 0. So the assumption is nicely specified. It's nicely sorted. Okay. Okay. Now you can plot the residuals too. So the next command will plot the residuals and see the other information. So this is the mean of the residuals. You can plot the residuals. Let's plot the residuals and look at it here. Okay. This is the residual plot on the right. When we start looking at diagnostics, you will understand this better. The residuals, okay, there's a line, and the residuals must always be seated, nicely horizontal to the line. There must not be any pattern of this. We'll come and check all these analyses. You can look at other plots. For example, multiple plots about the residuals, how it looks like. You can see so many things about the residuals. I'm not going to go. Yes, Emmanuel.
Doug, from the plot on the screen, as we have, is the residual the blue dots or the red line?
Okay, so the residual is showing you the fitted is a red line, the dotted line. Okay. And then the
residual are the blue dots. Okay.
The actuals are the blues.
Okay.
And the residual is the red.
Okay.
Which is showing you the difference between the horizontal one.
Okay.
And then the blue one.
The blue one. Okay. Okay. Okay.
So normally we expect it to be moving like the fitted.
The fitted. Okay. Yeah.
Well, there mustn't be any pattern along the line. Okay. But this one, you see patterns there. I will show you properly when we are looking at diagnostics, how these residuals are supposed to show. Anyway, the next command will show you the results in multiple graphs so that it becomes clear. So this is another plot of the residuals. When you do this plot, it gives you all the residuals for all of them. Different ways of looking at the residuals. You can look at the residuals versus the fitted. You can look at the residuals in a quantile normal probability plot, which is the one on the right. You can look at the scale and the location of the residual. Oh, by the way, it will also reveal whether there are some outliers or not. We'll look at all this later. As you can see, there are some of the observations that are consistently proving to be outliers, like number 2 and 40 and things like that. So these are some of the residual plots that you can deal with. Another of the residual plots is, or you can also look at the square of the residuals, the mean of the residuals, and several other things. There are other calculations that you can do to be able to check the sensibility, how sensible your entire model is. Now remember that we've not even interpreted the models. Next time we're going to interpret the models, and then we'll look at the diagnostics in all of them. The residual can help you to detect or correct nonlinearity. You can correct outliers. You can correct heteroscedasticity. Okay. We'll look at these one by one. Okay, all of them, we'll look at them one by one next time. So that is just the beginning of multiple regression. But please remember that we've not even interpreted the results. Okay. Now, there are other multiple regression results you can show. And I want to show that because I will explain the results and do the diagnostics later. So other multiple regression you can do. To do them, you have to install a package called library tools. Now, please note that this is going to give you the same thing we have already done, but in a different, beautiful way. That's all. Beautiful way. Okay, so I'm going to run the library J-tools. So to do that, you need to run the library J-tools first. Okay, mine says there's no package, which means I haven't installed it. So again, whenever you haven't installed something, you click packages and then you go and install. The package is J-tools here. So I click on it, I install the J-tools. Give it some few seconds. Depending on the speed of your internet, it will install the J-tools or the package that you're looking for you. Once it's done, you run the command. I just did. It shows down there as blue, which means that it's sorted. Now we are going to run the command again. The multiple regression. Watch the word. I called it gene multi, but this time under the summary, I didn't write the full name of the summary. I just wrote SUMM. Okay, because we are using a different package. And then I indicated that I wanted to give me some specific variables, results. I want you to give me a summary of the regression. The confidence interval is true. So I want you to give me the confidence interval. I also want you to give me the p-values. And the decimal point should be 2 decimal places. So you're going to run the OLS. But this has to be done with, there are 2 of them you should do. You should do the one with the nominal data, or you have to do one without the nominal data. So if I run this one right now, okay, it might not work. Maybe it works. Let's see. So I'm going to run this one. Okay, this one works fine. Okay. So look at this result down there in the console. It's a beautiful result. Okay. Let me tell you why it's beautiful. Because at the bottom, it will tell you that the model has 40 observations. Now, the previous one we used didn't tell us that. It will also tell you which one is a dependent variable, kill. What type of regression is using, OLS. Okay. It will tell you the F statistic and its p-value nicely. It will tell you the R-square and the adjusted R-square. Beautiful. So the way it gives you some kind of results are nice. It will also tell you the coefficients. It will tell you the confidence interval. It will tell you the T statistic. It will tell you the p-value. Okay. So it gives you some very nice results, in this case. Now you can see that it has given us the intercept. If you don't want the intercept, you can run the next command. This one. Okay, when you run the next command, it will give you everything without the intercept. So you can see that now it starts with the price. There is no intercept. And it gives you everything in this result. That is another model. Take note of what I just did. I just created another regression, the same regression, but in a beautiful look. Then I did the same regression again, but I excluded the intercept. But then we look at the write-up. If you want to exclude the intercept, instead of starting with P, you start with 0 plus P, which means you want the intercept to be 0. When you start with 0 plus P, you have it here in your slice. Okay, it means that you want the intercept to be 0. And then you can run your result. Another regression I want to run is called robust regression. Robust regression will report the standard errors. Okay. It is a beautiful regression. We'll talk about them next 2 weeks when we are looking at heteroscedasticity. There are several types of robust regression, standard errors. And we use the standard errors. It's the only thing you can change. You see, the coefficient you can't change. You cannot replace. So you can replace the standard errors. And when you replace the standard errors and you divide the coefficient by the standard errors, that will give you the t statistic. As long as you can alter the standard errors, you can get a different t statistic or t value, which will then give you a different p value. So the standard error correction is a big deal in econometrics. And this command will give you a robust standard errors. The HC3 is a heteroscedastic consistent standard error that corrects for heteroscedasticity. The C3, HC3 means there's HC0 all the way up to HC5. Okay. The 3 is the default, but if you understand the others, you can use the others. So that's it. You get this if you set the robust to true. Starter will use the HC1. Our R will use the HC3. So you may want to use the starter one if your goal is to repeat or replicate the analysis from starter. But whatever it is, I'm going to show you the robust. This is it. So look at the results here, the robust one. The coefficient will be the same, but the t value will not be the same. So look at the t value. Look at the original one. In fact, let me run the original one so that you can compare and see. They look slightly different results. So this one is OLS. Look at it here, OLS. Then the robust one. Where's that? Oh, I didn't run the robust one. Okay, so that's the OLS. Let me run the robust one. This is a robust one. Ah, okay. So the robust one, you don't get the results. You only get the what do you call it? If you want to know the result, just highlight it and show the results. That's it. Highlight rather and show the result. So I just did. So look at it. It tells you that robust and the type of heteroscedasticity correction is HC3. Okay. And when you compare the two, there's some interesting thing. For example, just look at the original OLS one. You see, the coefficient will be the same. Negative 3.15, negative 0.11, they are the same. Okay, they are the same. But look at the standard errors here. The first one is, for the intercept, is 32.38. Okay. Here, okay, so this one normally doesn't give you the standard errors. It gives you something else, but you can get it from the previous one. If you check the previous standard errors, it's different. Now, how do you know it's different? Compare their t values. Look at the price. The t value is negative 2.01. Look at this one. It's negative 1.92. Let's look at the next one. The next one for complement price is negative 2.79. When it comes to the robust, it's negative 3.65. So there are differences in the t value, which means that the p value will also be different. Okay. Some of the p values will be different. For example, this one is 0.05, but this one is 0.06. You know, this one is 0.01, but this one is 0.00. This one is 0.14, but this one is 0.20. This one is 0.19, and yet this one is 0.09. So the robust is usually better, as the name sounds. We know that the smaller the p-values, the better. And generally, most of the p-values in the robust will be closer to 0 than generally most of the p-values in the original OLS. So that's another model that we have been able to create, okay, the robust. There's another model that we can create with this data, which is called GLM. GLM is Generalized Linear Model. GLM. I don't want to go into the nitty-gritties of the GLM, but we'll look at GLS properly when we come to heteroscedasticity analysis. The GLM is another model you can use with this J2's package. It's beautiful. It saw some other things. And I'm going to show you final thing before we close. So I'm going to run the GLM. It's the same thing as everything. Instead of the OLS, which is LM, I do GLM here. And just run it. Okay. Let's see down here. I'm going to run it now. Okay. And you can see the GLM. Okay. It uses a maximum likelihood estimation. Okay. And maximum likelihood estimation is a very nice way of also finding the beta parameters. That's what it uses. It gives you other interesting things aside the usual F statistic. It gives you some chi-square distributed test. It gives you some pseudo R-square. It calls it the Gragola. It gives you the McFadden, several other R-squares. It gives you the Akaike criterion information, and then the BIC. All of these, it gives you, if you understand it, you know how to interpret it. Okay. Again, we'll look at most of them in diagnostics. It gives you all of that. This is another beautiful result that you are seeing right here. So that's called GLM. Now I'm going to put all of them together and give you a final table that compare models. And this is it. I'm going to put this table together here. To do that, you install a package, and again, you have it in your slides. The package is called HAX table. Okay, HAX table. So you install and load this package, HAX table. I hope I have installed. Okay, it says there is no package called HAX table, so it means you have to install. So click install, and then do HAX table, and then click install. Give it some few seconds. Depending on the speed of your internet, it's done. So you run the HAX table and watch it. I'm going to now run each model in a beautiful table all into one comparatively. Guys, this is beautiful. This is beautiful. So you write export underscore sums, the summary of the first model was gene multi, that's the OLS. The second model is gene multi with the intercept. That's how I called it, the intercept. The other one is gene multi, the robust one that I did. Okay. If you can remember the robust one. Then I also did the gene multi, the GLM, the generalized least square. I set the scale to the same thing. Then I run a table. Watch the table. There you go. Is that not beautiful? So the final table is this. And sometimes you read journals and you see them give you the results in tables. So model 1, you should know what it is. Model 1 is the normal regression. Okay. The model 2 is the one without the intercept. So you see that there is no intercept for model 2. So model 2, I could have chosen not to even break them. Model 3 was a robust. Model 4 was a GLM. Each one of them has got the coefficient, and below the coefficient, you have the standard error. Remember, the coefficient divided by the standard error always gives you the t statistic. The stars will tell you the level of significance that you are using. Each independent variable is on the left. At the very bottom, you have the sample size for all of them. You have the R square. Each one will give you the value of the R square. Some of them don't give you the R square value, like the GLM, because of its estimation using the maximum likelihood estimation. But it will also give you the Kaike information and other things. It has put a note down here that all continuous independent variables or predictors are mean-centered, scaled by one standard deviation. The dependent variable is in its original unit. So whatever units that you do, then you have this. The rest is interpretation, which we shall do next time. But ladies and gentlemen, there are some beautiful graphs that you can. So sometimes people mistakenly will do the work and then they will go and take it one by one to Excel and then blah, blah, blah. Look, this thing does it all here. Look at it. Does it all here. So you can just take this thing as it is straight into your Word document. And then you can have a wonderful, wonderful analysis right here, you know, with the work that you are doing. So let's say that I have some Word document here. I mean, there are several ways you can look at it, but this one is quite big. So normally you have to find a better way to looking at it. So I just want to pick everything as it is. But normally, in this case, I have to put my distance in, what do you call it, in portrait form. If you keep it in portrait form, it will look nicer than it is looking here. How do you even put it in portrait form? Let me see. I just want to show you that that's how you take it to portrait insert. I just want to have it in some sort of portrait.
I think you should go to layout.
Layout. Okay, good. There you go. Thank you. So you now have it in portrait form. Well, this doesn't look too great though. Let's see. If I can delete, I don't think that it will look any different. Yeah. But the next best option to do is that you can put it in Excel and then shift it back. So if you put it in Excel like this, and then you can do, where is that? You can do review. The review. You can do data and then text to columns. And then you can adjust them and help each one of them, hopefully, you start looking better than it is. Yeah. Sometimes you have to just adjust them the best possible way you can. But that's it. That's it. You know, it gives you a bit of, sometimes I will normally cut, but of course you can arrange them in the best possible way. There's a way to arrange them. Just escape. And then it will look very, very nice. Sometimes even the way it looks here, if you use a tab, you can squeeze them, then arrange them very nicely using your tab section. Then, and that will help you to be able to. And then you have the next one here. Okay, you can see that this one is in this format here. Okay, and then you can move the other ones concurrently into it and adjust them slightly. But there's a way, like I said, you can do that. So that is how it is. And then you can have a beautiful model for you to interpret. Next time we meet, we are going to look at how to interpret this whole model. Now, let me show you finally another table that can use to run this whole thing. That one will give the names. It will not write the word models. Okay. It will not just write models. It will give you the actual names. That's the last thing. It's called Stargazer. Stargazer. So you have to install Stargazer one time. If you haven't installed, you install it one time. And then you run it. Okay. I install Stargazer one time, you run it. And then Stargazer, you specify in the order in which you want it to appear. So this is the OLS. This is the OLS. Once you write this OLS, then the first labeling under the column labels, you write the name. You want the name to be OLS. The second one is the one without intercept. Okay. In fact, I'm going to remove the one without intercept because it's just not necessary. Okay. I'm just going to remove the one without intercept. So this second one here without intercept, I'll remove it. Then you have the GLM. Oh, where is the robust? Okay, so because the robust is not here, I can keep the one without intercept. So there are only 3 models. Okay. And the kind of things you want to have the sample size, the R squared, the F test, the log likelihood, the Kaki information, the BIC, the log likelihood ratio, and then the word test. We shall look at all of this, but they are into the area of GLM. And then you run this. And then you get that. This one is cool as well. See, this one, what it does is that it gives you for each one with the names. It doesn't only tell you model 1, model 2, but it tells you the model. This one is OLS. This one is OLS with no intercept. This one is the GLM. Okay. And you're able to have it all here. Okay. You can find a way to just take this one to it. And again, once again, you have the other information that should go. So when you're talking about the models, you can compare the models based on this beautiful results that you have here. That is how you do your analysis. And then you can interpret each of those results the way that you want in that regard. So that is how you do it. It appears that in this case, maybe when it comes, you have to transpose it, then it will look good. It will look good when you transpose it. But that is how you generate this thing in a beautiful table. The tables are Hacks table and then Stargazer. That is the way to run your regression. Next time we come, we are going to look at interpretation of the result. Ladies and gentlemen, that brings us to the end of the entire tableau.